All right, ladies and gentlemen, we're going to do another activity that shows how optical rotation can be used to determine the purity of a mixture of enantiomers. So what we have here is molecule X pictured here. I rotated this so it could fit. This is the reference value for the optical rotation. Reference. We don't use that till we calculate percent EE. We got to figure out the specific value of the rotation for the lab value that's right here. Remember, the units that have to be used for mass are grams, and we're often using milligrams in chemistry. And I like quarters and thirds and stuff like that. So how many grams is that as a fraction? Yeah, 1/4 of a gram. And then decimeters instead of centimeters. We have to do that. Remember, there's 100 centimeters in a meter, and there's 10 decimeters in a meter. So there's 10 centimeters in a decimeter, right? 10 times 10 gives 100. So how many decimeters is that? 2. So you're ready to set this thing up. We're going to do alpha. The specific alpha is what the square brackets mean for the observed rotation. Basically, we're standardizing the observed rotation, which was negative 2.60 in the question, original value in black, divided by grams per milliliter. 1/4 gram for every 10 milliliters times 2. Some simplification is in order here, isn't it? Sometimes people like to have the 2/1. Just to remind everybody, the 2 is in the numerator down there. Down here, there's numerator and denominator in the denominator. 2 times 1/4 simplifies to what? 2 simplifies to 1, and 1/4 simplifies to 1/2. And then let's see. Yeah, let's just deal with this. So when you simplify this, negative 2.600 degrees over 1/20. 1/2 over 10 is 1/20 times 1 equals negative 2.6 times 20, right? Well, 2 times negative 2.6 is negative 5.2, and then 10 more, right? Times 10. 1/2 divided by 10. 1/2 over 10. Well, you're dividing 1/2 by 10, right? That's 1/20. And that's going to be, well, 2 times 2.6 is 5.2, so 20 is 52 in the negative direction. Okay? So negative 52 is the specific observed rotation, and it's not as big as positive 130 or negative 130. It's not, so it's not pure. We know that. We can figure out how pure it is right now. Percent EE. You take the value you just calculated. Because in society now, I was asked this very important question. Why are we not allowed to use calculators? Because in society now, people are losing a sense of numbers and mistakes are happening. People are using calculators without thinking, and they'll miss a digit, and they won't even have a clue at the end because they didn't think about the numbers they were manipulating. Where you're doing it by fractions and estimating answers, you're getting a better sense of numbers. It's to make you a better scientist. That's why. Give a sense of numbers. So negative 52 over what it would have been if the stuff was pure, which is 130. And I want to make it that. And this morning we figured out that these don't look like nice numbers. Then again, I wasn't thinking about this. What's 13 times 2? 26. What's 26 times 2? Oh, 52. You know, this simplifies. I didn't see that this morning at all. They said, oh, well, when the numbers aren't nice, sometimes you estimate it. So I estimated 40%. It was 40%. Okay. All right. So, yeah, divide both of these by 100. Let's see what it was 13, right? Divide by 13. I know it's not obvious to see this. You divide that by 13, it's a 10, right? And this by 13 was a 4. And I don't care about signs anymore because of this, right? So forget about minuses and pluses. 4 over 10 times 10. 40% EE. Means only one thing. Here it is. You ready? There's 40% more of the major enantiomer than the minor. That's the interpretation. We haven't discovered, and we could have discovered which one was major and which one was minor right from the beginning. The signs don't match. Signs don't match. Therefore, enantiomer is major. If they matched, then molecule X was major. Good to know. We have 40% more enantiomer than we do molecule X. And let's break it down. 40% EE means 40% enantiomer. And what's the rest? 60% something. Don't say the 60% molecule X. Now you're telling me molecule X is major all of a sudden? Don't do that. Please don't do that. What does this 60% represent? It's the part that doesn't rotate light. The solution's behaving as if there's only X in there. It only behaves as if there's a 40% excess of X, or sorry, of the enantiomer, and the rest of the solution canceled each other. We had a name for that. Say it again? Oh, you got all the right letters. He anagrammed racemic. He said ceramic. I liked it. I love anagrams. Yeah, it's a racemic mixture for 60%. And I get students always asking me, where the heck did the 60 come from? 100 minus 40 is where I got 60. Okay, that breaks down to 30% more enantiomer. Yeah. And 30% molecule X. And that's all we're concerned about in this question. I always just ask about molecule X. I don't change that. We don't need any confusion last minute. This is the first semester he ever asked about the enantiomer. No, this won't be. Okay, I'm going to ask about molecule X every time. And so I just need to know what 30% of 250 milligrams is. Total, 250 milligrams. Hey, 10% is easy to do in your mind. 10%, 10%, 10%. Add them up when you're done. That's 30%, isn't it? Oh, I love breaking numbers down. What's 10% of 250? 25, 25, 25. 75 milligrams. is 40% EE. Okay. Oh, it's not, it's 30%. Wait, not 40%. No, I didn't want EE in the box. EE was the previous box. 30% X is 75 milligrams. 30% X. Let's highlight the answers where we got them from. If I wrote percent, maybe I could have remembered. There we go. Yeah. And there we go. This morning we did the same problem, except this was plus 2.6. Changes everything, doesn't it? The math is all the same, but we had, 175 milligrams of X, which was 70% this morning, right? Because the signs matched this morning. We had a plus here and a plus here. So X was major, and it was, 70 and 175. So watch that video too. And there we go.